Introduction to Quantum Information Processing. Welcome to Lecture 17 about distance measures between quantum states. We'll see various ways of quantifying how different two quantum states are, including the fidelity and the trace distance. I'll also show you the Holovo-Hellstrom theorem, which relates trace distance to the operational problem of distinguishing between a pair of states by a measurement. Recall that we consider two quantum states to be indistinguishable if, for any measurement procedure, the probability distribution of outcomes is identical between the two states. For example, if two pure states differ only by a global phase. Another example is these two probabilistic mixtures. We saw back in Lecture 14 that these two states have the same density matrix. When two states are indistinguishable, we don't even consider them to be different states. We say that two states are distinguishable if they're not indistinguishable. In other words, if for some measuring procedure, the outcome probabilities are different for one state from those arising from the other state. For example, the ket 0 and the ket plus state are distinguishable. Note that our definition of distinguishable does not require us to be able to perfectly tell the two states apart. Another example is this mixture again. Remember, I called it the fake plus state and the actual plus state. Finally, we'll define two states to be perfectly distinguishable if there is a measurement procedure that perfectly tells them apart. For example, the plus state and the minus state are perfectly distinguishable. These are three qualitative categories, but can we actually quantify how different two states are? An operational way of quantifying the difference between two states is based on the guess the state game that we've seen several times before. For any two states, which in general can be mixed states, imagine the game where Alice flips a fair coin to decide which of these two states to set a quantum system to, and then she sends the quantum system to Bob. Bob knows what the two possible states are, but Alice does not tell him which one she chose. Bob's goal is to apply some sort of measurement to the state that he received and to use the classical outcome to guess which state it was. We can write the success probability of Bob's optimal measurement procedure as 1 plus delta over 2, where delta is a parameter between 0 and 1. Of course, one strategy for Bob is to just guess a random bit and ignore the system that he received from Alice. That strategy succeeds with probability 1/2. We can think of delta as how much better one can do than that baseline. Another way of viewing delta is as the success probability minus the failure probability. It's sometimes useful to look at delta this way. For a given pair of quantum states, what's the best delta obtainable? If the two states are indistinguishable, then delta equals 0 is the best possible. At the other extreme, if the two states are perfectly distinguishable, then the success probability can be 1, so delta can be 1. An in-between case is when the two states are ket 0 and ket plus. These are not perfectly distinguishable, but the distinguishing probability can be as high as 1 plus 1 over root 2 all over 2. The distinguishing probability is approximately 85%. So delta is 1 over root 2. This delta is a natural way of quantifying the distance between two states. in terms of the highest distinguishing probability possible. Here's another example of a pair of qubit states that are mixed states. Alice flips a coin and, based on the outcome, prepares one of these two mixed states and sends it to Bob. Then Bob's task is to guess which state it was. You can imagine that if you worked hard at it, you might come up with a good distinguishing procedure for this particular example. But I've chosen this example so as not to have any special structure or symmetry that makes it simple. Also, suppose you came up with a distinguishing procedure that seems to perform well. How could you determine if it's optimal, or if there's a better procedure than the one you found? Later on in this lecture, we're going to develop a methodology for addressing these kinds of state distinguishing problems in a systematic way. Now, let's look at the distance between two quantum states from a different perspective, a geometric perspective. If we have two d-dimensional pure states, then it seems natural to take the Euclidean distance between the two d-tuples that are their state vectors. If their Euclidean distance is small, then it's intuitively natural to think of the states as close. But if their Euclidean distance is large, then should we think of the states as far apart? Not necessarily, because of global phases. Note that minus ket psi is the unit vector furthest away from ket psi, the Euclidean distance being 2, even though these are the same state. Also, it's not so clear how to extend this notion of Euclidean distance to mixed states. Another notion of distance is called the fidelity, which for pure states is the absolute value of the inner product between the state vectors. Here, fidelity 1 means indistinguishable, and notice that the absolute value takes care of any global phases. And fidelity close to 1 means that the states are close. What about the fidelity between mixed states? It turns out that there is a definition of fidelity for mixed states. If ρ0 and ρ1 are the density matrices of the two states, then the fidelity is given by this formula. I'm not going to explain it, but I want you to see it. It may look strange. Notice that you cannot cyclically permute the square root of ρ0 to the other side. This is because of the square root within the trace. One reasonable property that this has is that this agrees with the definition for the very special case of pure states. This is easy to verify, and I'll leave it as an exercise. After looking at that expression for fidelity involving all those square roots of matrices, let's think about what it means to take the square root of a matrix. This is part of a more general functional calculus on square matrices. Suppose that M is a normal matrix and F is any function from the complex numbers to the complex numbers. Then we can define F applied to the matrix M as follows. Since M is normal, we can diagonalize M in some orthonormal basis. Define F of M as the matrix where F is applied to each eigenvalue. If we want the square root function to M, then it's good for the eigenvalues to be greater than or equal to 0. In other words, for M to be positive. A word of caution. In general, for square matrices L and M that are positive, the square root of L times M need not equal the square root of L times the square root of M. This is because L and M may not be simultaneously diagonalizable. They are each diagonalizable, but not necessarily with respect to the same orthonormal basis. By the way, for a positive matrix M, it also makes sense to define M log M, which is related to the von Neumann entropy of a quantum state. We're not going to get into that here, but this will come up in a later part of the course. We can also define the absolute value of a normal matrix using the functional calculus. Just take the absolute values of all the eigenvalues. Notice that the absolute value of M is equal to the square root of M star M. This is interesting because M star M is always positive for any matrix M. So we could take this as the definition of the absolute value for any matrix, even matrices that are not diagonalizable. Now, I'd like to show you a very interesting distance measure between quantum states called the trace distance. First, I'll show you the trace norm of a matrix. It's the trace of the absolute value of the matrix. The notation is as a norm with subscript 1. Sometimes this alternative notation is used, where the subscript is tr. Notice that the trace norm of M is the one norm of the vector of eigenvalues of M. Okay, now we can define the trace distance between two states. It's the trace norm of the difference between their density matrices. Of all the different matrix norms on which we could base a distance measure on, what's so special about the trace norm? Why is this a meaningful measure of distance between states? The answer is given by the amazing Helleville-Hellstrom theorem. Remember the delta that arose in our definition of state distinguishability? We defined delta to be the advantage over random guessing in the guess the state game. In fact, that delta is exactly the trace norm multiplied by a half. So the trace norm coincides with how well the states can be distinguished in the guess the state game. Now I'm going to prove the Helleville-Hellstrom theorem. There are two parts, which I'll show separately. First, I'm going to show that there is a measurement whose success probability is 1/2 plus 1/4 times the trace distance. Then I'll show that no measurement can perform better than that. Let's start by showing that there exists a measurement whose success probability is 1/2 plus 1/4 times the trace distance. Let rho 0 and rho 1 be the density matrices of the states that we wish to distinguish between. Note that since rho 0 and rho 1 are Hermitian, rho 0 minus rho 1 is also Hermitian. But notice that because of the minus sign, it's possible that rho 0 minus rho 1 has some negative eigenvalues. Now consider two projectors, pi 0 and pi 1, defined as follows. Let pi 0 be the projector onto all the eigenspaces whose eigenvalues are greater than or equal to 0. Let pi 1 be the projector onto all the eigenspaces whose eigenvalues are less than 0. Pi 0 and pi 1 are orthogonal projectors, and they sum to the identity. Therefore, they specify a POVM measurement. We'll next show that this measurement succeeds with probability 1/2 plus 1/4 times the trace distance between rho 0 and rho 1. To prove this, first note that if we multiply rho 0 minus rho 1 by pi 0 minus pi 1, then we get the absolute value of rho 0 minus rho 1. Think of the matrices in diagonal form. Pi 0 minus pi 1 has plus 1 in the diagonal entries where the eigenvalue is greater than or equal to 0, and minus 1 in the diagonal entries where the eigenvalue is less than 0. So the effect of multiplying by pi 0 minus pi 1 is to flip the sign of the negative eigenvalues. Therefore, the trace of this is the trace distance between the states. Now, look what happens if we expand this expression. The first two terms, multiplied by a half, are the success probability. The second two terms, multiplied by minus a half, are the failure probability. So the delta, the success probability minus the failure probability, is equal to 1/2 times the trace distance. This proves the claim. Note that our proof of this part is constructive. It actually gives us a recipe to determine the optimal measurement for distinguishing between two mixed states. You consider the matrix that is one density matrix subtracted from the other density matrix, and then you take the projector to the positive eigenspace of this matrix and the projector to the negative eigenspace of this matrix, and those two projectors constitute the optimal POVM measurement. So far, we've proved that our particular measurement attains the proposed success probability. But how do we know that there isn't an even better measurement? Now we'll prove optimality. Let E0 and E1 be the POVM elements of any two-outcome POVM measurement for distinguishing between row 0 and row 1. We'll prove an upper bound on its performance. First, notice that E0 and E1 are simultaneously diagonalizable. Why? Because E1 equals identity minus E0. So if E0 is diagonal in some coordinate system, then so is E1. Please note that this only holds because it's a two-outcome POVM measurement. For POVM measurements with 3 or more outcomes, the matrices might not be simultaneously diagonalizable. Also, the eigenvalues of E0 and E1 are between 0 and 1, and they sum to 1. It follows that the largest eigenvalue of E0 minus E1 is less than or equal to 1. Let the infinity norm of a matrix M denote the absolute value of its largest eigenvalue. Incidentally, this is also the spectral norm, which is defined for all matrices, whether they're diagonalizable or not, though we don't need that here. In this language, we have that the infinity norm of E0 minus E1 is bounded by 1. Now we're going to make use of this lemma, which states that for any two normal matrices L and M, the trace of Lm is less than or equal to the infinity norm of L times the trace norm of M. Note that it is not being assumed here that L and M are simultaneously diagonalizable. I'm not going to prove this lemma here, but it's not very hard to prove. I'll leave it as an exercise. Now let's continue proving that any POVM measurement for distinguishing between row 0 and row 1 does not outperform the measurement that we constructed. Define A to be row 0 plus row 1 divided by 2, and B to be row 0 minus row 1 divided by 2. Note that row 0 is A plus B, and row 1 is A minus B. The success probability of the measurement is given by this expression, which is averaged over the probabilities of the input instances. Substituting the A and B in, we get this. The terms can be rearranged like so. And this is upper bounded by this. Notice that E0 plus E1 is the identity. Also notice that the latter part directly follows from the lemma that we just saw. And this simplifies like so, which is the upper bound that we are trying to prove. This proves the optimality, and we have now completed the proof of the Holevo-Hellstrom theorem. Next, I'd like to show you what a purification of a quantum state is. Any mixed state can be viewed as a pure state on some larger system with part of that larger system traced out. Let ρ be any density matrix of a d-dimensional system. Suppose it can be written as a probabilistic mixture of m pure states like so. Now consider this state on a d-dimensional register and an m-dimensional register. The square roots of the probabilities are the amplitudes, and note that there is a second register. If we trace out the second system, then we obtain the density matrix ρ. The pure state here is called a purification of ρ. This is one way to purify ρ, but the purification of a state is not unique. Now let's recall the previous strange-looking definition of fidelity between general mixed states that I showed you earlier, but which I didn't explain. Using our language of the trace norm, we can rewrite the expression this way. There's a theorem called Ulhmann's theorem, which asserts the following. For any two density matrices, we can take purifications of them and then take the inner product of these purifications. The result will depend on which purification we choose. Ulhmann's theorem says that if we take the maximum possible inner product by purifications, then this is equal to the fidelity. I'm not going to explain this further, but there is a reference below if you'd like to learn more about this. We've discussed fidelity and trace distance, mostly the latter. There are these known relationships between them. In particular, suppose we have two mixed states with density matrices ρ0 and ρ1, and we want to show that their trace distance is small. One way to do this is to construct purifications of them whose inner products are close to 1. By Ulhmann's theorem and the second inequality above, we have this upper bound for the trace distance. Please see the reference below for further information. Okay, let's end the lecture now.